Hello everyone, welcome back to IB360. Today we are diving into the IBDPSL Chemistry Paper 1 from May 2023 attempt. This will be applicable for all time zones, that is for EB and C. And if you're interested in personal guidance, you can consider joining my paid classes, or you can also have me as your mentor. You can just drop me a message on WhatsApp. So let's get started. So this is the first question. Which is the correct equation for electrolysis of molten sodium chloride? Molten sodium chloride is your reactant will be NaCl liquid because sodium chloride is molten. And during electrolysis, what happens is you get sodium solid and you'll get chlorine gas. Now to balance this, just we need to put a 2 here. So this will be my chemical reaction for the electrolysis of molten sodium chloride. And we see that this will directly match with option C. So option C will be the correct answer to this question. Moving on to the next one. We have to calculate the mass of one molecule of C60. Okay, so first we have to find the molar mass of C60. So molar mass or molecular mass. This will be 60 times the molar mass of carbon. So 60 times 12, you'll get 720 gram per mole. This is the molar mass of C60. Now, molar mass means this is the mass of 1 mole of C60 molecules. So mass of 1 molecule of C60 will be, this will be total molar mass divided by the Avogadro number. Because 1 mole of C60 will contain 6 times 10 to the power 23 molecules. So, yeah. And upon further simplification, we'll get this as 120 times 10 to the power of minus 23. So I can take in 2 decimals, I'll get 1.2 times 10 to the power of minus 21 grams. Right? Okay, so comparing the options, option B is the correct answer to this question. Now for question 3, 20 centimeter cube of gas A reacts with 20 centimeter cube of gas B to produce 10 centimeter cube of gas AXBY and 10 centimeter cube of excess gas A. We have to find the values of X and Y. So we'll first make a list. So volume of gas B, which reacts, this is basically 10 centimeter cube. Now volume of gas A, which reacts, this will be, see, you're initially giving 20 centimeter cube and 10 centimeter cube is excess. So what happens? 20 minus 10 amount reacts. So 20 minus 10, that is 10 centimeter cube. And lastly, volume of gas AXBY produced would be again 10 centimeter cube. A volume of gas B is 20. Okay, now we can design an equation or a reaction. A gas plus B gas, these two will react, give you AXBY gas. Now, if I want to balance this, I have to put an X in front of A and Y in front of B. Now, we can use the modified stoichiometric ratio to solve this. So, what's the modified stoichiometric ratio? If all your reactants and products are gases, instead of moles in the stoichiometric ratio, you can replace moles with volume. So, I can write volume of A reacted by volume of AXBY produced. This would be X over 1 because coefficient of A is X and coefficient of AXBY is 1. Now, volume of A reacted, I know the value is 10. Volume of AXBY produced is also 10. So, this will be equal to X. So, X is equal to 1. Done with the first one. Now, the next. We have to find the value of Y. So, for Y, we can just write the stoichiometric ratio between B and AXBY. The volume of B reacted by volume of AXBY produced. This would be Y over 1 because Y is the coefficient of B and 1 is the coefficient of AXBY. So, volume of B reacted is 20, AXBY produced is 10, this is equal to Y. So, from here, I can say Y is equal to 2. So, X equals 1, Y equals 2 is the correct answer. So, from here, option D would be the correct answer to this question. Now, question 4. So, here I'll just zoom in a bit. So, the volume V for a fixed mass of an ideal gas was measured at constant temperature at different pressures P. Which graph shows the correct relationship between PV and P? So, fixed mass of gas means your moles is constant. Constant temperature means T is constant. So, in the PV equals nRT equation, like nRT, these three are constant, so PV will be equal to a constant. So, the value of PV won't change even if you change the pressure and volume. Right? So, yeah. So, what happens is PV will be a constant. So, I can say option A is the correct answer, which will be equal to K. So, yeah. For question 4, A is the correct answer. Now for question 5, we have to state the correct ground state electron orbital configuration for 2s2 p2. So 2 electrons are there in the S subshell and 2 electrons will be there in the P subshell. Then the S subshell, because of the Pauli's exclusion principle, we should have electrons in the opposite spin. So if one electron is in the clockwise spin, other should be in the anti-clockwise. So here we see option C and D. In both these options, we see that the electrons are in the electron in the 2s subshell have the same spin. Now for for 2p, what happens is we have to first singly fill the orbitals of 2p. Then we'll start pairing. Now for a general convention, what we do is we singly fill the subshell with electrons in the same spin first, and then we start pairing them with the opposite spin. So with our natural general convention, we can say A will be the correct answer to question 5. Now moving to question 6. So basically you have two cases here. First, a hot gas cloud is emitting light. Another one is a light source. You're giving this light source towards a cold gas cloud, and then light is coming through it. So which type of spectra are associated with light passing through cold gas? Spectrum A and the hot gas spectrum B. So clearly from spectrum B, we are getting emission spectrum. Emission spectrum occurs if you already have a heated object which is emitting light. And in this one, we will have absorption spectra for this part when light sources pass and when light is passing through a cold gas cloud. Because here light is emitted when the energy is absorbed. Right? So A will be absorption, B will be emission. So answer is option A. Now question 7. What is the electronic configuration of element in group 4 period? We take help of the periodic table. Yeah, we've made some calculations before, so I'll quickly clean this up. Yeah. So group 4 period 5 is this element zirconium. Okay. So yeah, so the nearest noble gas or the noble gas just before zirconium is krypton. So first I'll try to write the electronic configuration of krypton. Krypton will be argon. After argon, 4s2. This is still calcium. 3d10. This is still zinc. And then 4p6. This is still krypton. So after 4p6, we need to know which subshells will be filled next. So yeah, if I come here, these won't be the answer. Answer will either be A or D. Now we can use the Aufbau principle to identify that. So for Aufbau, I'll draw the checker box. 3D, 4s, 4p, 4d, 4f, 5s, 5p, 5t, 5s. This much will be enough. So first your 1s subshell is filled, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, and 5s, then 4d, 5p. So the krypton was still, if you have checked, krypton was still 4p. So after 4p, you will fill 5s, and after 5s, you'll fill 4d. So 5s and 4d are next to 4p. Now how many electrons do we need to fill? So there are 4 valence electrons in zirconium. After 36, we need to fill 4 electrons. So yeah. So 2 electrons will go in 5s and 2 electrons will go in 4d. The answer should be krypton 5s to 42. 42. That is option A. Why did I fill like this? So first 5s will be filled. So 5s has 1 orbital, so 2 electrons will go there. Then you'll start filling the 4d. 4d will have 5 orbitals, but you just have 2 electrons, so all the electrons will go in the 4d. So yeah, the answer is option A. Now moving on, which properties increase down group 1 alkali metals? Now atomic radii. Atomic radii definitely increases because as we go down the group, number of electron shells increase. As the number of shells containing electrons will increase, your atomic radii will also increase. So this is true. Now for melting point. Melting point, what happens is for alkali metals, melting point decreases as you go down the group. We go down. So this will be false. And the last one, reactivity with water. What happens is as you go down the group, your ionization energy decreases. So as the ionization energy decreases, it's easy to remove the electron from the outermost shell. And because of that, you can say reactivity increases. Going down the group. Hence, reactivity increases. This one is also true. So from here we see that option 1 and 3 are only true. So I'll go with option B, which is the correct answer to this question. Now moving to question 9, we have to identify which compound is soluble, is both volatile and soluble in water. So we can make kind of a table. So yeah, NaCl is soluble in water, but it's not volatile. Okay, like you can check salt water is never volatile. CH3, CH2, CH3. Then organic compound. So it is not soluble in water or neither volatile. So CH3OH. CH3OH is an alcohol, so it will be soluble in water, and alcohols are actually volatile. It is an informative question. So yeah, option C gives us both ticks. So option C will be the correct answer to question 9. Question 10. Which are the correct sequence increasing bond strength and bond length between two carbon atoms? Basically, the thing is C triple bond C is stronger than C double bond C, which is stronger than C single bond C. So obviously these two options are wrong. So yeah, anything between C and D. Now, thing is bond length is inversely proportional to the bond strength. Bond strength. So the one having the highest bond strength will have the shortest bond. So C triple bond C will have the shortest bond, then C double bond C, then C single bond C. So you can say option C is the correct answer to this question. Now moving on, what's the electron geometry of sulfur dioxide? For that, you have to first find out the electron pairs around sulfur. Sulfur in SO2. So we'll use our formula half times. First, we have to find the number of valence electrons on sulfur. So sulfur has 6 valence electrons. Plus, there is no monovalent atoms attached to sulfur. Monovalent atoms means atoms which make single bonds. So oxygen makes double bonds, so no monovalent atoms. There is no negative charge and no positive charge on SO2. If I simplify, number of electron pairs is coming as 3. If your number of electron pairs is 3, the electron geometry would be trigonal planar. Trigonal planar, which is option D. Now moving on, question 12. You have to compare the bond angles in NH2 minus, NH3 and NH4 plus. The first NH4 plus. NH4 plus is a complete tetrahedral structure with no lone pair, right? So NH4 plus will have a bond angle of around 109.5 degrees because it's just tetrahedral with no lone pairs. No lone pair. Now if I look into NH3, what happens is NH3 has one lone pair on top of it. So because of the lone pair and bond pair repulsions, what happens is these bond angles will shrink a little. So here the bond angle will approximately be equal to 107 degrees. So again, here the molecular formula will be pyramidal, but it has one lone pair. So because of that, your bond angle has decreased a bit. And for NH2 minus, it will look like this. So you have 2 electrons now. So the lone pair bond pair repulsion will be even higher now. So this bond angle will be even less, somewhere around 103 degrees. So we see NH2 minus has the smallest bond, followed by NH3, and NH4 plus will have the largest bond. So NH4 plus, NH3, and NH2 minus, which corresponds to option A. Now, in this question, you are given the enthalpy of formation of ammonia gas. You have to calculate the energy released because of this reaction. So first, write the formation reaction of ammonia gas. The enthalpy of formation is given for the reaction where only 1 mole of the product is formed. Okay, the stoichiometric coefficient of ammonia should be equal to 1. So it will look like this. So your final product is ammonia gas. It will have half N2 gas plus 3/2 H2 gas. The enthalpy of this reaction is minus 46 kilojoule mole inverse. Now what happens to get this reaction? We have to multiply 2 on both sides. So if I multiply 2 on both sides of this reaction, what happens is I also have to multiply the enthalpy with 2. It will be N2 gas plus 3H2 gas, which will give me twice NH3 gas. This is my required reaction. And our net energy or net delta H will be minus 46 times 2. That is minus 92 kilojoule mole inverse. Negative 92 kilojoule means 92 kilojoules of energy will be released. Okay. Of heat will be released in this reaction. From the options, option D will be the correct answer. Now here we have to find the delta H of this reaction, of this given reaction, and yeah, obviously it's a Hetzloff problem. So for this, I'll have to check the relative positions. N2H4 is on the left, NH3 on the right. So I can write the first 2 equations as it is. So I can write N2H4 liquid, or let's just ignore the states for now because it's not really required, plus CH3OH. This will give me CH2O plus N2 plus 5H2. The delta H will be minus 37 kilojoule for this reaction. Now again, I'll write the second reaction as it is. Delta H will be minus 46. Now say in the first reaction, you have CH2O on the right and CH3OH on the left. But here in this reaction, again, you have CH3OH on the left and CH2O on the right. But you see, you don't have CH3OH and CH2O in the final equation. So what happens? I have to cancel these 2, right? To cancel this, I have to reverse the third equation. That's the main thinking here. This will give me CH3OH. What's the delta H? If I reverse the reaction, delta H, I mean, the minus 65 will become plus 65. Minus of minus 65, that is plus 65 kilojoules and kilojoules again. Now, if I add these three reactions, let's see what gets cancelled out. So the 3H2 on both sides will get cancelled out. CH2O will get cancelled out. CH2OH will get cancelled out. The N2 also will get cancelled out. So finally, I'll be left with N2H4 plus H2, which will give me twice NH3. Okay. And delta H of this reaction will be the sum of all these enthalpies. Is minus 37, minus 46, plus 65. So if I perform these calculations, I'll be left with minus 18 kilojoule mole inverse. Okay. So from here, option A is the correct answer to this question. Now question 15, which statement concerning bond breaking is correct? So bond breaking requires energy. So you have to provide energy in order to break a bond. So it requires energy. So yeah, and a reaction. So requires energy means you have to supply reaction, and the reaction will absorb the energy. So in a reaction where energy is absorbed, it's an endothermic reaction. So 15 will be option A. Now 16. This is a little controversial question. So you have a curve X shows volume of oxygen produced during catalytic decomposition of 1 mole per dm cube solution of hydrogen peroxide. So basically, we are tracking the volume of oxygen found with respect to time for this reaction. Right. So thing is, X was the actual reaction. Okay. Now I have to produce the reaction. I mean, I have to produce this curve Y by changing some of the reaction conditions. So these are the conditions given. So we have to identify. So see, more volume of oxygen gas is produced. That means what? More moles of H2O2 has reacted. Yeah. So let's check the options. If I add more water, what happens is the concentration of H2O2 falls. And also here, you see the initial rate or the slope of this curve here is much steeper as compared to the slope of the curve in the original X. So yeah, the reaction is becoming faster. That's one. Okay. The observation will be reaction is faster. And second one is more volume of O2 evolved. Now, repeat the experiment without a catalyst. This is wrong. If you don't apply a catalyst, I mean, the reaction will become slower. If I add water, the concentration of hydrogen peroxide will fall. If concentration falls, then obviously, the reaction will never become faster, and the moles all will remain the same. So we cannot. I mean, more volume of oxygen cannot be evolved if I add more water. Now in B and C, both the options, we are adding some more hydrogen peroxide. I personally feel because the initial rate has increased so much, we might have to put a little bit more hydrogen peroxide. So I would say option C would be the answer. So if we add 2 mole per dm cube hydrogen peroxide, what happens is the concentration in the solution increases. As the concentration increases, the rate of the reaction will be faster. Okay, and obviously more volume will be evolved. But yeah, I'm not 100% sure. It can also be option B. The final answer key has not been released yet. So probably it will be released in the coming Monday, or which is tomorrow in my time. So yeah, I'll update. I mean, if there are any changes, I'll update them in the description. Now moving to question 17. A potential energy profile is drawn for a reaction, right? And yeah, what energy changes would a catalyst affect? So first, we have to understand this is the enthalpy. Okay, this is the activation energy of the forward reaction. This is the activation energy of the reverse reaction. Okay, now catalyst decreases activation energy. So this will be your new activation energy, you can say. So guess what? If this is the new activation energy, your activation energy of the reverse reaction also decreases. Activation energy of the forward reaction will also decrease. But you see the enthalpy of the reaction will remain the same. So yeah, your catalyst will affect 2 and 1. So which is option A. Which condition will cause the given equilibrium to shift to the right? Okay. So one by one, 1/2 solid EgCl is removed. This can be the correct answer. We'll first check the others and then continue. So if water is added, what happens is concentrations of Ag plus and Cl minus will form. Or you can also say in this way that the moles of Ag plus and Cl minus will remain constant. So yeah, obviously, definitely in this case, the reaction will not shift to the right. Okay, so this is not correct. Solid NaCl is added. Now thing is, you have to add aqueous NaCl, right, in order to increase the Cl minus ion concentration, which can help you move the reaction towards the right. But if you are adding solid NaCl, what happens is in this case, no Cl minus ion is added to the solution. So obviously the equilibrium won't be affected here. Now system is subjected to increased pressure. Again, won't be feasible here because pressure differences will only be make some difference if you have a gas. And in this reaction, you have two aqueous solution and one solid solution. So yeah, there will be no effect here. So from this, I can say option A is the best option to question 18. And obviously, if you keep removing solid AgCl, what happens is like more and more AgCl will be produced. So you're removing AgCl. Now this one, which reaction represents the neutralization reaction of a Bronsted-Lowry acid and base? Now, coming to this is an addition reaction. Addition reaction is not a neutralization reaction, so this is wrong. NH3 is a base, okay? And this is oxygen. So this is basically an oxidation reaction, but not, you see, there is no transfer of H plus ion or acceptance of H plus ion. So this is an oxidation reaction. So again, I'll ignore this. I'll check the first and the second one. For the first one, there is electron transfer. Because see, Zn is losing 2 electrons while hydrogen is gaining 2 electrons. So we can maybe write a Lewis definition here, okay? If you want to say like which one will be a Lewis acid, Lewis base, it can be done. But it won't be a Bronsted-Lowry acid or base. For Bronsted-Lowry, your H plus ion, I mean, there should be an exchange of H plus. This is a Lewis acid base reaction. Now coming to option B. Option B is kind of working for us because see, HCl, from HCl is donating H plus ion, right? This is the H plus donor, or this is acting as an acid. ZNO, like if you dissociate it, Zn2 plus and O2 minus. O2 minus will accept this H plus, right? So basically your ZNO is acting as an H plus acceptor. And finally you are getting H2O as a product, and the Cl minus and Zn2 plus will combine to form ZnCl2. So yeah, we found both the H plus donor and both the H plus acceptor in option B, right? So I can say option B is actually the neutralization of a Bronsted-Lowry acid or base. Now, the hydroxide ion concentration of a solution of pH 4. Okay, so pH equals 4. This means, guess what? Minus log base 10. H plus ion concentration is 4. So, log base 10 H plus ion concentration will be minus 4. If I take 10 to the power on both sides, so your H plus ion concentration will be, okay, this is a negative 4. Be 10 to the power of minus 4. Now, I know for any solution, where water is a solvent, at 298 kelvins, the H plus ion concentration and the OH minus ion concentration would be the Kw. Kw is a constant. It's called the ionic product of water. Ionic product of water has a constant value at 298 Kelvin, which is 10 to the power of minus 14. The H plus ion concentration is 10 to the power of minus 4. OH minus ion concentration, this will be equal to 10 to the power of minus 14. Okay. So from here, OH minus ion concentration will be 10 to the power minus 14 divided by 10 to the power of minus 4, which is 10 to the power minus 14 times 10 to the power of 4, which is 10 to the power of minus 10. So option D is the correct answer to this question. Now moving on, which element has variable oxidation states in its compounds? Now potassium and calcium will form only one ion. Potassium can only form K plus ion, and Ca will only form Ca2 plus ion. So these two will definitely not be the answer. Fluorine is the most electronegative element in the periodic table. So again, it can only have one oxidation state, which is -1, which you get in like the F minus ion. Okay, one oxidation state which is -1. Here it's +2, here it's +1. But for bromine, you can have multiple oxidation states. For example, Br minus, okay, BrO2, BrO3 minus, okay, and BrF3. I can write more compounds here. So in these compounds, you see bromine has variable oxidation states. So from this, I can say D is the correct answer to this question. Now, which chemical processes would produce a voltaic cell? So what happens in a voltaic cell? Voltage is generated. So in your syllabus, you have two types of cell. One is a voltaic cell, where you are getting energy out of a reaction, and then you have electrolysis, where you are putting in energy to drive a non-spontaneous reaction. So if you have a voltaic cell, your reaction has to be spontaneous. If you have a spontaneous reaction, then only the reaction will keep going on and it will keep providing you energy. So yeah, these two will be cancelled. And for a voltaic cell, you'll always see voltaic cell is applicable for redox reactions. There will be spontaneous plus redox reaction. So combine them. Option A is the correct answer to this question. Now the next one, which species could be reduced to form SO2? So basically, we have to check which species here, in this species, sulfur has a greater oxidation number than SO2. Then what happens? If you're converting that species to SO2, there will be a reduction reaction. So first, let's calculate the oxidation number of sulfur. Let's take it as X. X plus 2 times -2 equals 0. So oxidation of sulfur here is +4. Oxidation of sulfur in SS is 0. Now this one, I'll again take sulfur's oxidation number as X. So hydrogen is +1, sulfur is X, which is unknown, and oxygen is -2. This will be -6 plus 2. This is -4. So X is +4. For option B, the sulfur has the same oxidation state as the SO2, so it's not, we cannot reduce it. H2SO4, let's try. Again, I'll take the oxidation state of sulfur as X. No, it's not X plus 6, it's X minus 6 equals 0. So X is plus 6. So in option C, we see that H2SO4, the sulfur in H2SO4 has a greater oxidation number as compared to sulfur in SO2. So what we can do is we can actually reduce this to form SO2. So option C is the correct answer to this question. Which compound is an aromatic ester? Nice. So for an aromatic ester, you should have a double bond O, C double bond O, R1, R2. Okay, so this is the structure of an ester. So yeah, the first I will cancel this because this is a carboxylic acid. You have to test for the rest now. Now, aromatic ester means either your R1 or your R2 should be a benzene ring. Has to be a benzene ring for the ester to be aromatic. Now see here in option C, it's an ester, but there is no benzene ring, so I'll cancel C. For option D, you see this is not exactly a benzene molecule. Okay, benzene molecule will have C6H6, like a structure, a hexagonal structure like this. So yeah, we in this case this is an ester, but it's not an aromatic ester because it's not attached to a benzene. So in only option B, you have a benzene attached, and you have the C double bond O, single bond O, CH3. So option B would be the correct answer to this question. The next one, which products could be obtained by heating isomers? Okay, let me bring it down a little bit. Yeah. Which products could be obtained by heating isomers of C3H8O under reflux with acidified potassium dichromate? So first, let's see what structures are possible for this. The C3H8O. So you can have this thing. Okay, this can be one isomer. Another isomer is this one. These two isomers are only possible. Right? Now, if you heat them with acidified dichromate, K2Cr2O7, the compounds will start to get oxidized. So this one will have only one product, that is a ketone. This ketone is called propanone. So propanone is there, 2 is there. Now, if I oxidize the first one, first it will produce this, which is the aldehyde. Okay. Then it will keep reacting with K2Cr2O7 to give you carboxylic acid. This is called propanoic acid. And this is propanol. Now, the most important thing, it is heated under reflux. If you want to keep the aldehyde, you have to heat it alongside, you have to distill the compound. Distillation means you are removing the aldehyde as soon as it's formed. Okay, but if you reflux it means you are again introducing the product stream back into the reactant mixture. So in that case, what happens? All the propanol which is present, it will get converted to propanoic acid. So it will be impossible for us to obtain propanol if we are refluxing it. So we can only have propanoic acid and propanol, which is 2 and 3. So option C will be the correct answer to this one. Now question 26. What is the preferred IUPAC name of the following structures? So I have to number it. So we can number it in 2 ways. 1, 2, 3, 4. Okay. So if I number it in this way, we have 2, 3, 3. Let me just write it. So this way. So numbering from left to right, we have groups 2, 3, 3. And if I number it from the right, I'll get 1, 2, 3, 4. From the right, it is 2, 2, 3. So by the the lowest locant rule, I'll choose this one because 2, 2. There is a clash. Ignore 3, 2. Between 3, 2, 2 is lower. So I'll choose this one, or we'll number from right to left. Okay. Now, what is left? At 2 and 3, we have 2 methyl groups. So it'll be 2, 3 dimethyl. Now the word root, you have 4 carbon atoms, so the word root will be but. All single bonds between the carbon, so butan. And the OH is present at 2, so butan 2-ol. So 2, 3 dimethyl, butan 2-ol, which is option B. Now the next one, what are most likely reaction ethene and benzene will undergo? So ethene has a double bond. As ethene has a double bond, it will be far easier for us to add compounds to ethene as compared to substitution. Right, so BR. So ethene will show addition reactions. So I can ignore these two. Now benzene. Benzene generally shows substitution reaction. Okay. Even when you H2SO4 HNO3, what happens is this hydrogen gets substituted with the NO2 group, which gives you nitrobenzene. So yeah, benzene generally shows substitution, while ethene generally shows addition, which is option E. Oh, sorry. The next one. Now this one is again a little bit, I can say a little weird question. So which observation would explain a systematic error for an experiment involving the combustion of magnesium to find the empirical formula of its oxide? So yeah, so here in this case, what happens is we measure everything based on the empty dish, right? So first, before starting the experiment, we measure the mass of the empty dish. Okay. Then we put in the magnesium in the empty dish, and then we measure the mass of this is the magnesium, right? Mass of Mg plus empty dish. So how do I get the mass of Mg? I'll simply subtract this mass, mass of the empty dish from the mass of Mg plus the empty dish. Okay. Now after this, after we heat this, basically what happens is, like inside you'll have magnesium oxide, right? So this thing here is your MgO. We'll measure this mass. So this will be mass of MgO plus empty dish. Okay, so again we can subtract the mass of empty dish from the mass of MgO plus empty dish to get the mass of MgO. Right? So yeah, that would be our experiment. Now let's check the option. This crucible lid was slightly ajar during the heating. So this won't make any real difference. If you are heating it at a very high temperature, then in that case magnesium will start reacting with the nitrogen, but eventually inside the container you'll have nitrogen. So ignore this. The product was a white powdery substance, and this won't form an error because like magnesium oxide is a white powdery substance. The flame color during heating was yellow. Okay, I can ignore this. But crucible had a black soot on the bottom after heating. After heating, you had some black soot here, which is because of the flame. Now, what happens if you have black soot? Then there is an error here. Now you have some extra black soot, mass of black soot, which we will generally not, generally not take the mass of this black soot in our calculations. So this is a systematic error. So from this, option C can be the correct answer to this question. Now 29, we have a graph that shows the concentration of C4H9Cl versus time. We have to find the average rate over the first 800 seconds. Average rate in the 800 seconds will be minus, So it will be negative, or we can use this formula, negative of delta C4H9Cl divided by delta T. So first, concentration of C4H9Cl at time 800 seconds minus the concentration of C4H9Cl at time 0. First 800 seconds, so from 0 to 800, and the time will be 800 minus 0. So this one, the concentration is 0.02. The concentration of C4H9Cl at 800 seconds is 0.02. Concentration of this at 0 second is 0.1 divided by 800. So this will be 0.08 by 800. So 0.01 times 10 to the power of minus 2. So 1 times 10 to the power of minus 4. This will be the answer. So, which is option B. Now moving to the last question. Which compound will have only one HNMR signal and show a carbonyl group in IR spectrum? So one HNMR spectrum means there is only one hydrogen environment. In CH3CHO, these three hydrogens will be in the same environment, but this hydrogen will be in a different environment. So here you have two hydrogen environment. Moving on to the next one. CH3COOH. Here, these three hydrogens will be in the same environment. This one, this one, this one. But this hydrogen will be in a different environment. So again, you have two hydrogen environments. Two hydrogen environment means you'll have two NMR signals. Okay. And the next one. Now here, you will only have one hydrogen environment. Please, if I can cancel out. Okay, so both of them, like, all the hydrogens here will be in the same environment because it's a symmetric structure, right? But there is a problem. What's the problem? The problem is that it should contain a carbonyl group. Carbonyl group is a C double bond O, right? But there's only C single bond O here. So again, I have to reject this. Now we'll try the last one, which is a ketone. So here in propanone, again, you see propanone is a symmetric structure. Draw the line of symmetry from here. Guess what? You have only one hydrogen environment. So this one has one hydrogen environment, and you also have a carbonyl group present. This is the carbonyl. So option B will be the correct answer to this. So yeah, with this we come to an end to our paper 1 of NEET 2023 attempts. So as the answer key or the mark scheme isn't out yet, so there might be some differences, but Yeah, I'll keep you all updated in the description. Okay. Thank you so much, and I'll post the paper 2 solutions really soon. Goodbye.